Okay, so in the videos you went over, we described the other section of piping systems, which is the cases where we have minor losses. So in this section, we'll develop techniques in order to account for minor losses in piping systems. And we'll see that the presence of minor losses will complicate analysis and it will be more difficult to solve for our unknowns. Okay. Let us consider the following problem. A huge water reservoir is drained with a 2 nominal schedule 40 galvanized steel pipe that is 60-meter long. هنا they are giving us the total length of the pipe. The piping system is shown in the figure. The fittings are regular and threaded. Determine the volume flow rate through the system if Z1 is given to be 5 meters and Z2 equals to 2 meters. So whenever you have such figure, the first step will be to determine you want to apply your energy equation between which levels. So here we will start first by saying that we know the elevation Z1, we know the elevation Z2. We also know the conditions because point 1 is subjected to atmospherical pressure, and point 2 we have exit of flow also at atmospheric pressure. So already we know a lot of conditions at points 1 and 2. We can say already that P1 equals to P2 equals to P atmospheric. Okay, and we have the change in elevation here is driving fluid motion. If you remember last time when we considered an example of horizontal piping, we have seen that in this case, in order to have motion of the fluid, the driving was the pressure drop. Here, because you have this difference in elevation, this will create the potential of flow because the gravitational energy will be transformed into kinetic energy when going from 1 to 2. Plus, of course, we'll have here to account for losses. A part of this energy will be lost because of the major and minor losses. Now, we know also the levels Z1. So Z1 is 5 meters. Z2 is 2 meters. And whenever you have a large reservoir, okay, you have a free surface and the section is relatively much higher compared to the section of your pipe system, you can consider that V1 is can be approximated by 0. Why? Because you have continuity. From continuity equation, you have that the mass flow rate is conserved. So you can say that rho V1 A1 is equal to rho V2 A2. Since it's an incompressible flow, rho will not change. So rho will cancel out. And you can say, because A1, the area at section 1 is much larger than the area at section 2, I can say that V1 is much smaller compared to V2. And then we can approximate it by 0. Okay, so until now, we have information about pressures, we have information about elevations, we just don't know what is the velocity of the flow at stage 2. So this is the first unknown we will deal with. Now, when we write the energy equation, the second step will be to write the energy equation. When I want to write the energy equation, I should account for major losses and minor losses. So already for major losses, I know the total length of the pipe. And I know that major losses are in the form of F times total length over D hydraulic diameter. But here it's you have a circular pipe. So it's you take the diameter of the cross section of the pipe times V square, okay, over 2G. So this is the expression of the major loss. It depends on V, and V will be equal to V2. Why? Because as you have the flow through your piping system, you are not having any change in cross section. So since the cross-sectional area is constant, V will not change from the point you enter the piping system until the point you exit it. Okay, so I'm dealing here with the same unknown as the exit velocity. Okay, now concerning lengths, I know it. Concerning D, also they gave me the nominal diameter and the schedule. This will allow me to find D. So I just have to determine what is my friction factor. Okay, and of course my friction factor will require the knowledge of two inputs, because to use Moody diagram I need epsilon over D. So to get F, I need epsilon over D, and I need Reynolds, but Reynolds is function of V. So from here I need to perform some iterations, because F function of epsilon over D, which is known, and of Reynolds, which is unknown. So I don't know F, I don't know Reynolds, since Reynolds is directly related to velocity. So I should perform iteration procedure to get my friction factor. Now, this is not the only challenge. I have also minor losses. Let us see together what are the sources of minor losses in this problem. Here, this figure, as you can see, this is what we call a basket strainer. It's like a system with a filter that will eliminate particles, so it will reduce, if you want, possible contamination in water. So it will filter out particles that can be harmful, so you have clean water passing through your piping system. And this is already an accessory that will lead to minor losses. So first we have a first source of minor loss is a basket strainer. In general, whenever you have something new in the figures that you are not familiar with, it will be described for you. And I will tell you in the given, we use at the inlet, when taking water from the reservoir, we use at the inlet of the piping system a basket strainer, and I will give you the minor loss coefficient of this basket strainer. It will be given for you, okay? Unless you can find it in the list of tables of minor loss. Together we'll go over a sheet that I prepared for you, and I will post it for you on e-learning for different accessories. What is the coefficient of minor loss? Okay, so this is the first source of minor losses. Now, as I go through my system, first I have a 90 degrees elbow here, and I have a second one here. So 1, 2, 3, and 4. And since I am changing direction in 90 degrees, so all of these 4 elbows are 90 degrees elbows. So I have first a basket strainer. I have 4 90 degrees elbows. I have also a valve here. Okay, I have a valve in my system. And always, okay, whenever you have exit from a thin section to the atmosphere, you have loss. You have what we call K exit. And we'll see together how to determine these coefficients from appropriate tables and sheets. Okay, so now I will go with you over a sheet that I will post for you on e-learning. That is, if you want, it's called minor losses. It will give you several tables and graphs, allowing you to determine the minor loss coefficient for any accessory you might find. And in case one of the accessories is not included in this sheet, I will provide you with the coefficient directly in exam. So here, for example, this is the basket strainer we were talking about. You can find it directly in the first table. So in the first table, already they give you familiar accessories that you can use in your system. Let's say if you have a basket strainer, you select 1.3, let's say. Sometimes your inlet is not, your inlet shape, for example, is not like straightforward like this. So you can have, for example, what we call square-edged inlet. So you have like a square here, contouring the inlet. So this form will have a certain minor loss coefficient. It's given. You can have different geometries for your inlet, and each one is characterized by a certain minor loss coefficient. So, for example, re-entrant inlet or inward projecting pipe is characterized by k equal 1. You can have a smooth transition in your inlet, and this is expected to have a small k. Why? Because in general, we have minor losses whenever any sudden change will cause a large minor loss. This is why here, since it's well-rounded, so you have a smooth transition for the flow when coming in your pipe. So you can expect that because of this geometry, K will be much lower. So as you can see, for well-rounded inlet or a bell mouth inlet, you can get a coefficient that is much smaller, a loss coefficient of 0.05 compared to 1 for re-entrant inlet, or compared to 0.5 for square-edged inlet. Okay. Now, we have also several types of valves, and each valve will be characterized by a certain minor loss coefficient. But as you can see here, for your exit, also you have, for example, for a normal exit like this, you can take K is 1. Okay. You might have nozzles in your system. If you have a nozzle, so you have change in cross section, you are going from a certain diameter to another one, to a smaller one. You have, as the name indicates, it's conversion. So you have reduction in diameter. Then you have a formula depending on the ratio d2 over d1. Okay, you can calculate the corresponding value of the minor loss coefficient. And as expected, كل ما الراتيو is small, the coefficient K بيزيد لأنه you will have like it will be more sudden variation in diameters. Now, for your elbows, whenever you have an elbow, you should determine first if it is the angle of your elbow, if it is 90 degrees or 45 degrees. So how am I changing the direction of the flow? What is the angle of change of the flow? Let's say in this, it will be clear from the figure. In the system we have always change in this problem as 90 degrees. You can have some elbows just changing the angle by 45 degrees. So this will be a 45 degrees elbow. Plus, we categorize elbows depending on the type of assembly with the piping system. So if we have threaded elbows, or if we have flanged or welded or glued elbows. If you remember in the chapter of accessories, we defined what are the different types of elbows and what is the way of assembling them, or if you want putting them in the piping system. All of these, so the technique of putting the accessories with the system will also affect the minor loss coefficient. Okay, so you can see here a lot of accessories in these tables. For example, you can have 180 degrees return band. It also will create a certain loss, and it depends, it's threaded or flanged, welded, etc. You have the T-joint accessory having specific coefficients also. So we have a lot of types. You can, all of them will have their corresponding expression of minor loss. We talked about also, if you remember, the reducing bushing, in which you have reduction in diameter. So also you have a certain formula for the minor loss coefficient depending on D1 and D2. For example, for the convergent nozzle, you have like a gradual change. So this will help into reducing K. However, if you do a sudden reduction, then you expect to get larger values of Ks. And here also we have, depending on the type of valve used, it's a globe valve, it's a gate valve, it's an angle valve. In general, we should tell you the type of the valves to know which one to select. Or sometimes, as we'll see after, you have symbols. And this symbol is for, let's say, open valve or gate valve. So from the symbol, and I will give you graphical charts to tell you how we present valves, how we present accessories. So then you can read, if you want, a map of piping systems and understand each symbol is for what. Okay, so here, going back to our figure, after we determine the sources of minor losses, we can say that I have as total, the total minor loss in my system is by accounting for, first, the basket strainer, which we already found together in the minor losses sheet, that its K is 1.3. You have 4 90 degrees elbows, and here's I told you that all of the elbows are regular elbows. So if you go back to the given, they mentioned that the fittings are regular and threaded. So if you go to your minor losses sheet again, and when you go to elbows, you should check for regular elbow and threaded ones. So here, this is regular. So first, this is I select 90 degrees. This is regular, this is threaded. So I select K 1.4. So I should have, since I have 4 elbows, I do 4 times 1.4, plus for the basket strainer, it's 1.3. We have also a globe valve in this problem and an exit. The exit, as we said, it's a normal exit. And from the figure here, you can say that for a normal exit, K is 1. And for your globe valve, if you check with valves, okay, down. So as I said, all are regular and threaded. So I select the globe valve that is K equal to 10. Okay. So now I know all my minor loss coefficients. I sum up them and I find the total minor loss coefficient. Now I am ready to proceed. I collected all information needed. Of course, as usual, for example, when they give us the nominal diameter, the schedule, I go to what? I go to appendix D1, okay, to select what is D. I can get D from there. So let us refresh our memory how to do it. We go to appendix D1. So nominal diameter 2, schedule 40. Since we are dealing here with SI units, so we can read accordingly the inside diameter of our piping system. And of course, we can calculate the flow area or take it from here. It's pi d square over 4. So this is for the diameter of our piping system. And concerning galvanized steel pipe, this information will help us into getting epsilon. So we go now to list of tables available, also posted on e-learning. From this list of tables, so let me show you, I posted for you tables of chapter 3. So let me check if I find it here. Anyway, it's posted on e-learning. If I don't find it now, you can just check chapter 3 tables, okay? And you will, it's here. So if you check this table, you can get the corresponding value of epsilon for galvanized material. Okay, so until it's opening. Okay, so we have galvanized steel pipe from which we will get epsilon. So now we have everything. We used all information in our given. We are ready to move to write our energy equation and see what are our unknowns. So let us write our energy equation. Okay, you have the following. First, we use the modified Bernoulli equation to take into consideration all sources of losses. So we have, as I told you, G sub C, you don't have to worry about G sub C. In SI units and in English units, it's 1. Just if you use English engineering, it's not 1, but in general, in this course, we deal with or English units or SI units. So directly you can substitute G sub C by 1. Hatta no need to put it in your equations. Okay, but just to know what is the meaning of it, this is a coefficient due to if you want the transfer of units in English engineering. In English engineering, G sub C is not 1. So this is why we put it to have for this formula to work in all types of units. So now the first term is P1 over rho G plus V1 square over 2G plus Z1 equals to P2 over rho G plus V2 square over 2G plus Z2 plus major losses, which is FL over DH V square over 2G, and summation of minor losses, which is sum of K V square over 2G. Now, next step is to replace variables by the values we already know. We said that P1 and P2 are equal. These two terms cancel out. Z1 and Z2 are known. We just replace. We are using SI units. We replace Z values in meter. We said that V1 is very small compared to V2. We neglected. So we end up with the following relation, that the change delta Z, okay, the change in Z or Z1 minus Z2 will drive the flow. So Z1 minus Z2 is the driving for the flow here, because this energy, so this gravitational energy will be transformed into a kinetic energy in a part and will overcome losses. It should overcome both major and minor losses. Okay, so now if I replace sum of K by its value that I got from the different coefficients, okay, I obtain the following Bernoulli equation. So the following Bernoulli equation will tell me that Z1 equals to Z2 plus FL over DH V square over 2G, okay, plus sum of K V square over 2G. Now, once I write this equation, okay, then I have to determine what are my unknowns here. I don't know the friction factor, and I don't know the value of my velocity. Okay, here there is a typing error. It's not true that V2 is 0. Okay, so please keep in mind. هلا بظبط لكم اياها انا. This is wrong. V2 is not 0 because you have velocity. You have the exit velocity here. Okay, you have the exit velocity at this level. So you should take into account here that you have rho V2 square over 2G. Okay, so now we got a relation. Okay, we got a relation between F and V. This is the important. Once we get a relation between F and V, so this equation will be called equation number 1. Okay, so this is equation number 1. Now, the next step the next step will be to, if you want, try to relate the Reynolds number to velocity, because already I have v function of f, okay? And I want to use the Moody diagram. To use the Moody diagram, I have f, I have Reynolds, I have epsilon over d. Okay, I have values for epsilon over d. For epsilon over d, there is no problem for me, because if I go to the table now to get epsilon, I have from this table that for galvanized steel, which is the material of my pipe, I can read the corresponding value of epsilon. Here, whenever you have in general, they will, if you have a range or take the middle, or they should specify for you, and they should give you information to be able to exactly do your selection. Okay, if not, you can take like an average value between the two extremes given, or they specify in the given then if they want you to take a certain particular value of epsilon for the corresponding type. So now, once we determine epsilon over d, and we just have to continue by iteration. We cannot solve by just using these equations, because you have f unknown and you have v unknown. Okay, and you just have v, you can express v function of f, but if you don't use an assumption, you cannot continue, because Reynolds is also a function of v. So this is your second equation, and this is your equation that you got from the energy is 1. So in these two equations, you already have 3 unknowns, f, v, Reynolds. So you need a third equation, or you need the Moody diagram, because Moody diagram is like a third equation for you, and it will allow you to iterate, okay, to perform your iterations. So what you can do here, you will say, I know v function of f, and I know Reynolds function of v. Let me assume f. Okay, I assume f. If I assume f, I can go to this equation and calculate v. And once I calculate v, I can compute Reynolds. Okay, now I have Reynolds and I have epsilon over d. Let me go to Moody chart to find for this Reynolds and this epsilon over d, what will be f. I can, from Moody, determine f from Moody. Okay, now what should I do then? I should compare my assumption to f I got from Moody. Is it close? Fine. It's not, I update the value of f. So I take now the new values from Moody diagram of f, and I repeat the process. I replace into equation 1, I get v. I replace v in equation 2, I get Reynolds. Okay, and then I will repeat this procedure until getting 2 consecutive values of f that are very close to each other. Once I reach 2 values that are where the relative difference, let's say, is below 5%, I can stop. Or sometimes they tell you the stopping criterion. They tell you stop when you reach a relative error of 10%. Then you stop. Okay. So let us see together, if you want, the details of these iterations. So let's say from calculation of epsilon over d, we have 0.00003. Okay, then we should go to Moody. So I will write the values here. And if you remember, we talked about a hint to assume f whenever we have epsilon. Okay, so knowing epsilon over d will allow us to do a certain approximation for f by taking the flat turbulent region. So if I go now to Moody diagram, I can say a good assumption to start with. So this is Moody. Okay. This is a Moody diagram. Here they don't put all curves. Okay, let me open another one. I know this second graph, if you remember, I cannot use this one. Okay, I cannot use this graph here. If you remember, we did last time together an example on modified Moody diagram. In this modified Moody diagram, I have here Reynolds to the power f half, which is not my case. So let me go to the Moody diagram, the conventional one. I can find it here in the course material somewhere. Okay. This is, for example, this is a Moody chart. So I have 4 zeros, 3. Epsilon is very small, epsilon over d. Epsilon over d is 3 times 10 minus 4 minus 5 لأنه عندي 1. I should multiply by 1, 2, 3, 4, 5 to get. So it's 3 times 10 minus 5. I can read it here, nearly here. Okay. This is, if you want, epsilon over d. This is my flat plate. This is my flat plate in turbulent region. هلا حتلاحظوا لأنه epsilon over d كتير صغيرة، the flat region منا is relatively narrow. بينما كل ما كبر epsilon over d, you will see that the flat plate range بتصير أكبر. So this is why it is easier to converge whenever you have high epsilon over d. You can start by assuming a value of f, let's say here, around this level, okay? And you say, let me replace the value of f in equation 1 to get v, in equation 2 to get Reynolds, and then go back to my Moody diagram to find updated f. So here, this is what they did. Okay, so a trial and error process will be required. First, we assume a value of the friction factor corresponding to the fully developed turbulent flow value, okay, for which in this case we can calculate the corresponding f. This is the corresponding f مثل ما شفناها أنا وياكم على الفigure. So then I will do a first ما بعرف هون شو عاملين صراحة، يعني في شيء غلط. I will check it for you. هيدي epsilon over d is here إلا إذا هون مغلطين بالcalculation because they are putting two different values. Okay, هيدي problems from the book, but they might have done a certain error. I will fix it for you. So once you get the value of f, so the first trial for you is f equal, let's say, 0.009 that you got from the flat plate region. Now you, if you substitute, you get v from in the first equation. You substitute v in Reynolds, you get Reynolds. Then let us go now to Moody and update the value of f. So we have Reynolds number equals to 8.53 times 10 to the power 4. إذا مظبوط الكالكوليشن تبعهم. Let us check شو حيطلع ال corresponding value لل updated f. So I go back to my Moody diagram. In my Moody now, I will take Reynolds equal to 8 times 10 to the power 4. So as you can see here, هيدي 10.5 يعني تقريبا هون تقريبا 8.5 here. Now if I follow my curve, I should follow these two curves. أول شيء هحط اللاين للرينولد تقريبا like here nearly, okay, and I will draw in another color a line للepsilon over d. So as you can see بعدت عن الانيشال assumption لأنه already هي منا كتير flat. ما في إذا بدكم الكيرف منا كتير flat أول شيء. So it's changing rapidly. This is why you can expect إنه اول iteration حتكون بعيده شوي عن الفاليو. So if you go تقريبا I can read the updated value 0.02. So now once I get the updated value I will repeat the same procedure. يعني going back to my analysis. Okay, as we said, it's very close to 0.02. أخذوها 0.019. So I replace now F in equation 1. I get updated V. بتلاحظوا إنه في فرق شوي بعد. Okay. هلا if you هلا مزبوط بالvelocity يمكن يطلع لكم فرق وبالرينولد، بس أنتوا you should look at the difference بالfriction factor mainly بالفريكشن فاكتور. اذا طلع لكم من المودي الفريكشن فاكتور تقريبا هو ذاته، يعني هلا هيدي الفاليو هي المضبوطه. اوكي، هي already بعيده عن الفيرست ترايل لانه it's expected because F are far from each other. اوكي، والرينولد كمان بعاد عن بعض لانه الفيرست والسكند ترايل كانوا الفريكشن فاكتورز بعاد عن بعض. So now we should with the updated values of Reynolds وابسلون اوفر دي انه نجيب الاف الجديده. اوكي، so now if we get a new f هتكون very close. يعني فينا نجربها اذا بنروح على الجراف مع 7.1910 تقريبا حنكون very close to the other points. Let us see it. So if you go to the figure again صارت عندي 7 times 10 for الفاليو للفريكشن. اوكي، بس بعدها كثير قريبه، يعني مضبوط. يمكن الريلاتيف ديفرنس بالرينولد شوي منا كثير صغيره، بس بالاف حتكون اصغر. يعني if you go to the figure and now you search على ال 7 times 10 to the power 4 حتكون هون تقريبا. Okay, and then if you follow your curve تبع الابسلون over d نفس البوينت تقريبا. It's nearly same point اللي هو على 0.02. اوكي، فانتوا بالريلاتيف ديفرنس بتضلوا تكملوا لحديت ما الاف ما تعود عم تفرق. بطلت الاف عم تفرق. So now if you plug الاف الجديده يعني بدل 0.019 تحطوا 0.02 او 0.0195 if you replace again هيطلع لكم nearly very close values لل previous ones. خلص ساعتها you can stop. Okay, so here you say I can stop now لأنه if I update here بعد ما أجيب الفاليو الجديدة. okay, if you update V و you update Reynolds هيطلعوا nearly the same value. You can check this. okay, فيكم من الأساس ما تجيبون لأنه بتقولوا بما إنه 0.0195 is very close to 0.019 خلص no need to get a new V or new Reynolds لأنه already the difference بيناتهم very small, so it's expected إنه